Okay, so what we have proved is the following. If we have an operator T in B of H, which is self-adjoint, then there exists, then we have an isomorphism, there exists an isomorphism P from C of sigma T to the C-star algebra generated by T, maybe add one. Okay. There exists unique such that which we call as F going to F of T. Okay. We call that as F going to F of T. Such that P of that identity function, that F naught, equal to P, where F naught of P equal to P. Further, this is what is called continuous functional calculus. Further, there exists a measure mu on sigma T and an isomorphism, maybe you call it P tilde from L infinity of sigma T with mu into B of H. And this is also unique. The exists a measure is not unique, the phi is unique. Unique such that phi tilde restricted to C of sigma T is that phi, and it satisfies the convergence criteria. Okay? And the strong convergence. I will not write it again. And the strong convergence criteria. So this is what is called measurable functional calculus. Why there is two different things? Of course, the measurable functional calculus is just an extension of continuous functional calculus. But the thing is, if you have a just a C-star algebra, then if you have a Banach algebra, you can, if you have an analytic function and you properly defined on the neighborhood around the spectrum, then you can talk about the function of that element, f of x. Similarly, if you have a C-star algebra, if you have a normal element, then you can talk about continuous function of that. And if you have a phenomenal, this is supposed to be from the phenomenal algebra. This is supposed to be, the range is supposed to be what is a phenomenal algebra. So if we have a phenomenal algebra, you can use the measurable function, a more general thing. That is one thing. The second thing is, you have to remember that these are all function space. These are all up to equivalence class, right? These are all not really functions. Okay. So that difference is there. For example, here you may identify, here it's a single function, but here it is defined on the equivalence class. You may identify function and they may give the, the difference is there. You will see that difference, how it works. Okay. So this is one thing. I want to give an assignment. It's very easy. Just you have to identify things and it will follow. Okay. I have already given some assignment. This is in addition to that. So is it this following? So if you have a T is in, this works for normal also. If the same proof works for normal element later. When we do spectral theorem for normal operator, and the same fact and same proof will work. Okay. So if a T is in B of H self-adjoint, and if you have a F from sigma T to C continuous, okay, continuous function. And if you have a G should be defined as G should be sigma of F of T. So sorry. Before that, I want to say the following. The assignment, this is not assignment number 1. There is just a observation. Okay, maybe call it 0. You can convince yourself. I will tell you the proof orally. You can convince yourself. The proof is this is what is called spectral mapping theorem. We have seen a spectral mapping theorem for polynomials. This is spectral mapping theorem for functions, continuous function, which works for here also, measurable functions also it will work. Spectral mapping theorem. I will erase this. It says the following. So which says f is a continuous function. F is from sigma T to C. Okay. Then, of course, you can, when you have a continuous function, you can define the functional calculus, and sigma of F of T So you can define f of t. You have a continuous function, you can define f of t. Sigma of f of t is f of sigma of t. This is clear because, so this map is, I mean, this f going to f of t is an isomorphism. Okay. So f of t and f as an element in a C-star algebra. C of x is C-star algebra. We have defined spectrum for C-star algebra. And spectrum of f of t is same as spectrum of f in C of x. Spectrum of f in C of x is f of sigma of t. Right? I mean, spectrum is just the range of the function. Okay? I mean, whether you have, I mean, f minus that element should not be invertible. It happens only if it is in the range of that. Okay, so from that it forms. Okay. So this is 0. 1 is if I have a f from sigma t to c, and you have a g in sigma of f of t, of course, to c, I mean, c is in c of sigma of f of t, which is of course equal to, which is equal to f of sigma of, maybe I'll just write it less, c of f of sigma of t, which is equal to c of sigma of f of t, of course. Okay. Then what do I want to say? I want to say that g, so what do we have to apply? So f, will take it here, and g of f of t. F of t is an operator. Okay, g of f of t, you can talk about f of t as an operator, and f of t, f of t is an operator. G is a function defined on the spectrum of f of t, right? So this makes sense, and that is equal to g of f acting on t. That's all. You, I mean, use the uniqueness of the phi, uniqueness of the functional calculus, and then exactly write the definition, you will get it. I mean, this is a unique thing which takes this phi of f naught to t. Right? So here the functional calculus which should take this function to the corresponding function. I mean, the inclusion is like this. You have C of f of, I mean, you have C of sigma of t, right? C of sigma of f of t, or f of sigma of t, the same as that. And from here, you can define a map to C of sigma of t. From here, if you have a g here, you can take to g of f. I mean, if g is a function from sigma of to something, I mean, f is a function, or f is a function from sigma t to f of sigma of t, then g from here to here, I mean, the other map will be on the reverse direction, right? So from g to g of f, you can define. This will give you a homomorphism. This will give you a homomorphism. And this includes that here. And use the functional calculus to get it to C star of t. On the other hand, C star of generated by f of t, this is certainly contained in the just inclusion map. This is contained here. And you have the map here. This map is nothing but this map. That is because I mean, because the isomorphism is unique. Right? I mean, from here, I mean, this is precisely that inclusion here. You can prove it. That's because it takes I mean, because of these properties. It's unique and it satisfies this property. Using that, you can prove. Okay? And second thing is, for the measurable functional calculus, there exists here. So if again, I mean, we assume that you can prove it for measurable functions also, but let us assume for only continuous function. F is from sigma of t to c, continuous. Okay. And this is the assignment. And okay. Then then there exists, I mean, then there exists a p tilde from L infinity of f of sigma of t. Okay. And with the measure, you can, when you have a function, you can define a measure, no? By taking the inverse image. I hope you know that. Okay. So which is equal to mu f inverse, which is called mu f inverse, okay, which is a measure. Okay. from here to that B of H, such that it satisfies the usual, I mean, the property for this. You know what the properties are. Please write. I don't want to write down. I mean, I want you to write on the, because there is nothing in the assignment otherwise. The property is it takes that I mean, the F naught to the operator T, okay, and it restricts to the functional calculus, and it satisfies that convergence, all that, okay. I mean, the map for this F of sigma T, the corresponding measurable functional calculus, this phi tilde, okay, that is given by this measure. That's what I want to say, okay. That is one thing. And it satisfies the same property there. And for all for G in L infinity of what is it, F of sigma of T, and that, I mean, the measure is up to defined up to equivalence, okay. This is one such measure, okay. We have G of F of T is again G of F, okay? Same thing. That's what I want to do. Okay? In particular, if we have a, I will use it for polynomials. If you have a F in C of sigma of T, again, T is self-adjoint, another thing. So sigma of T, then, I mean, so you can, for any measurable function, you can talk about the function of that operator. In particular, you can talk about 1e of T, okay, for any e in sigma of T measurable, okay. If you have any measurable set, you can talk about this. So I want you to prove that 1 F of E, I think this just follows it. F of E, F of T is nothing but 1. And this is what I want to do. Just to verify this. It's a direct verification. Use the definition, you will get. Is it right, what I have written? I think so. Check what I have written. There may be, if there is a mistake, you tell me. I think this is okay. Yeah. As functions, see, as functions, 1 E of F of E is just 1 E F, no? Right? Is it right or it's not? I'm just saying that if you take set E, then 1 E F, I mean, this takes the value 1 if F of T is in F of E. That doesn't mean T is in E, you know? So yeah, there is some confusion about it.
1 E of F of T equals 1 of the single flow.
Right. 1 E, say it again, 1 E. Ah.
1 of single flow.
I think this will work. Yeah. Yeah, this will work. Okay, this is what I mean. Okay, correct. Yeah, this may not work. Correct. Thank you. Yeah, just verify this. Yeah. But this should be, I mean, for all E in this, for E in F of sigma, and for all E in F of sigma.
Yeah.
Okay. Yeah, this will work. Yeah. I mean, that okay, yeah, property of the function, that will not work. Yeah. Of course, it will work if it's a nice function, injective or, I mean, it's if it is bijection, it certainly works. Yeah. Okay, so this is the assignment. So, and these are all remarks. The first remark is, so you can, of course, one ET is a projection. So, okay. And if E intersection F is empty, if E and F are disjoint, okay, as sets they are disjoint, then 1E times 1F equal to 1F times 1E equals 0. Okay. This implies 1E as projection, they are orthogonal to 1F. Okay. So disjoint sets will lead to orthogonal projections. See, so I didn't do all that, but I hope you should know by now. Must have studied enough projection in the graduate analysis too, I think. So if you have two projection P1, P2, P1, P2 is a projection if and only if they commute. Okay. We can write the properties of projection. I mean, the definition of projection, it will follow from that. I mean, of course, it has to be self-adjoint. P1, P2, if it is a projection, it has to be self-adjoint, so it will follow. And if P1, P2 is a projection, P1, P2 equal to P2, P1, then you can prove that this is a projection and all that. Okay, the product. So they have to commute. Otherwise, it's not a projection. Only commuting things. I mean, only when they commute, the product is a projection. Okay. So, but here everything commutes. So this one thing is this. I mean, here this is the commutative C-star algebra. Okay. So if we take any measurable, any two functions, they commute as functions, of course. So the product of function commute. So all measurable, I mean, f of t and f of g of t commutes for any f and g. Okay, they're all commuting operators. So because of that, one e and f they commute, and if e intersection f is empty, then so I mean, two projections are disjoint is equivalent to saying p1 p2 equals 0. Okay. Two commuting projections refer to, I mean, they are orthogonal if p1 p2 equals 0. So this is what it is. So if e intersection f is empty, then 1e, this is the notation. 1e is orthogonal to 1f. That is, the ranges are orthogonal. Okay. That is one thing. And second thing is, if, for example, if you have En increases to E or Fn decreases to F as sets, okay, then you can see that 1En, then of course 1En will converge to, I mean, you don't even need that. This is a stronger criterion. I mean, even if it converges in measure, it will follow. So if you have some sets, I mean, if mu of En, I mean, this will follow from that. Okay? Mu of En, the E, you know, the symmetric difference, which is equal to En minus E minus En, union of En minus E. If this goes to 0, okay, then this is not assignment, this is just remark, okay? So then, mu of this set where 1En minus 1E is greater than or equal to epsilon. Of course, these are all indicator functions. These are all characteristic functions. So if they are greater than or equal to epsilon, that has to be 1. Okay. That, I mean, so this is just 1 of En, okay, equal to 1, of course. I mean, this is 0 except this set, right? Except this set, no? Yeah. Only in the, yeah. Okay, only in the, so yeah, in this set, this is equal to 1, of course. So this is equal to mu of this, En, the symmetric difference. Okay. So this goes to 0. So if the symmetric difference, the mu of the symmetric, so this is the like a metric on the collection of Borel sigma algebra, but it's not actually a metric in the sense you have to identify sets up to measure 0. Then it will be a metric. Okay. And this gives this metric gives rise to the convergence in measure. Okay. So mu of En, the symmetric difference goes to 0, then En E goes to 0. Okay. Then this goes to 0. So this will imply that 1 En, I mean, this implies that 1 En T will converge to 1 Et strongly. Okay. By our criterion. Of course, these are all bounded functions. So 1 ENT will converge to 1 ET, right? So if this condition holds, then this goes to this strongly. And in particular, if En increases to P or Fn decreases to F, then 1 En T, which are projections increases to 1 E, not 1 Fn. I mean, what does it mean by projection increases? You take this is a projection, you have the range of this projection, Hilbert space. You take the range of En, range of 1 ENT will be contained in 1 EMT if N is less than or equal to M. And their union, you take the union and take the closure. Okay? I mean, usually if you take two subspace, union is not a subspace, but when it is increasing, it will be a subspace. You take the union, this just says that 1 ET. I mean, if Pn increases to P means you take the range of Pn, okay, and union of that and take the closure. That will be range of P. Okay? I mean, when I say Pn increases to P as projection, the range of Pn, which are subspaces, you take the union of all of them and take the closure, that will be range of P. Okay? So that is what it means. 1 ENT converges to 1 ET if En converges to En increases to E and Fn decreases. This is intersection. Okay, 1 ENT goes to 1 F. Okay, this just says that range of 1 ET equal to union of 1 ENT N, take range of this closure. And here range of 1 FT equal to intersection of, here you don't need to take the closure of course, intersection of 1 Fn, range of 1 Fn. So this is clear from that, of course. I mean, this is finite measure. If E and Fn decreases to F, then the mu of Fn will decrease to mu of F, so that satisfies. Okay, so these are all the remarks. Now I want to use the continuous functional calculus and define what is called positivity, okay, of an operator. So proposition T is in B of H. The following are equivalent. 1. There exists a S from H to another Hilbert space K. K is some other Hilbert space, okay, such that T equal to S star S. Okay. This is positivity. 2. T xi is greater than or equal to 0 for all xi in H. Okay. Third condition. So I forgot to say self-adjoint. I said self-adjoint, but I forgot to write. T is self-adjoint. T is an operator which is self-adjoint. Okay. No, I don't think, I mean, I'm going to write self-adjoint, so it's okay. It's not needed. No, this follows its self-adjoint, so it's okay. It's not needed. Okay. So T is self-adjoint and sigma of T is contained in 0. Okay. Fourth condition, there exists a self-adjoint. I've used yes there. So T, S, R, S, T, okay, R in B of H such that T equals to R square. So all these four conditions are equivalent. Okay, proof. 1 implies 2 is clear. It is just T looks like S star S means S star S xi equal to norm F xi square greater than 0. Okay, 1 implies 2 is clear. Okay, we know this. So 2 implies 3. So if T xi is greater than or equal to 0, we have already seen that if T xi is real, I mean, this is for all xi, T xi is real, then it is self-adjoint. We have already seen that. Okay, T equal to T star. Okay, so T xi, this inner product is in there, implies T is self-adjoint. So we have to only verify that sigma of T is contained in 0 infinity. And for that, you have to use the, I mean, This is the exercise. We have already seen used it for self-adjoint, the same proof. Self-adjoint and unitary also, I think I gave it as an assignment, I think. So, I mean, if this is greater than or equal to 0, then use the approximate eigenvalue. T is self-adjoint. In particular, T is normal. So every eigenvalue, if something is an eigenvalue, if and only something is in the spectrum, lambda is in the spectrum, if and only if lambda is an approximate eigenvalue, use that to prove this. We have already seen this. So from that, the second thing will follow. Okay. So sigma of T contained in 0 infinity. We have already seen this proof. Okay. This exercise. Now 3 implies 4. T is self-adjoint and sigma T is contained in 0 infinity. T is self-adjoint. Use the functional calculus. Sigma T is contained in 0 infinity. So you have a function f from sigma of T to, of course, 0 infinity itself, which is given by T going to T power half. You have this function. Okay. Now f of T square is exactly, I mean, f of T is equal to, so if S is equal to, R is equal to f of T, then R square equal to T. R square equal to, I mean, T, right? F square is the function T going to T. So that corresponds to the operator T in the functional calculus. So R square equal to T. That's our second step, right? This says that T is self-adjoint and sigma T is contained here. Since sigma T is contained here, you can define a function on sigma of T, which is the square root function. And square root function, square is the function T equal to T. And from that it follows. So we have to prove 4 implies 1 is clear. You take the, I mean, there exists a Hilbert space K and such that this happen. You take the same Hilbert space and, I mean, you take the same R square is R star R. Okay. So there is nothing. So if I mean, so any operator satisfying these 4 conditions is called a positive operator. If you want, you can write it definition. P is positive. Usually this is the definition without referring to anything. Okay. So it will satisfy all those conditions. So next proposition is P in B of H is positive. Then there exists a unique yes in B of H, which is positive. I mean, the same thing, I'm just writing it for the purpose of recording. But this is unique, the unique S which is positive, such that S square equal to T. A proof, you already defined that condition for, I mean, existence for of previous proposition. Okay. So 4 of previous proposition says that there exists a yes, and that is positive, of course. I mean, sigma of T power half is T of, I mean, square root of sigma of T. We have, I mean, we have this condition, no? F of sigma of F of T is F of sigma of T. So that F of yes, whatever we have defined that will be going to be sigma T half. Okay? It will take the square root of that, okay? Because of that. So which is again contained in positive, so it will be positive. From whatever the conditions we have, it follows that S is positive. Because sigma of S is also, sigma S is self-adjoint, and S is the sigma of the spectrum of S is contained in the positive real line, so it's positive. Okay, from the previous proposition, the existence is clear. We have to prove the uniqueness. So suppose there exists a S1 in B of H, such that S1 square, S1 self-adjoint, S1 positive, S1 greater than or equal to 0 is positive, S1 square equal to T. So, I mean, there exists a S, which is given by that, and also a S1, which satisfies this condition, S1 square equal to T. Okay. Now, T is written as S1 square. So, T is in the C star algebra generated by S1. Okay. T is equal to S1 square. Okay. So, in particular, C star algebra generated by T is contained in C star algebra generated by S1. Right? I mean, this is the smallest C star algebra containing S1. Okay. So T is contained, T is here means the C star algebra generated, no, sorry. This is the smallest C star algebra containing T. Okay. And this is a C star algebra. So this C star T will be contained here. Okay. Right. So C star algebra T is contained in C star algebra S1. Okay. And also we have that original S, that S. S is in C star algebra of T. That is why we have chosen it, right? Okay, maybe if you want, we can write it. There exists a self-adjoint R, where R is in the C star algebra generated by T, if you want. That's what we have defined it through functional calculus. So it is in the C star algebra generated by T. Okay, maybe I can add it. Okay. That's okay, no? R is in the C star algebra, whatever this S, whatever the initial S, which is just a square root function. I mean, square root function, using the square root function of the T, okay? I mean, if f is the square root function, f of t is that S. Okay. So that is in the C star algebra generated by T. So S is in C star T. So this implies this S is in C star algebra of S1. So there exists a G, we haven't used F anyway, there exists a G function in C of sigma of S such that G of S1 is equal to S. But now G square, I mean S square equal to the T, which is equal to G square of S1, right? This implies G is, because it's all right. Wait. No, S1 square, sorry, S1 square equal, sorry, S1 square equal to T, which is equal to G square of S1. Okay. So this and this are equal. In particular, we have S1 square equal to G square of S1. Okay. So this implies the, I mean, this is the of T square. This is in G square. Okay. So this implies G is equal to T because sigma of S1 is contained in positive real line. You take the square root and it has to be T. Okay. So this implies, I mean, so G of T is nothing but so this implies has to be equal to S. I mean, uniqueness of the functional calculus. Okay, so uniqueness is clear. So for positive operators, there exists a unique positive square root. I mean, whatever the properties we have a real function, it will be satisfied. This says that, I mean, not just within the C star algebra, even for operators, even in B of H, there is, I mean, this is the point of the proposition is this, yes, I mean, this uniqueness is in B of H. Okay. And there shouldn't exist something else in B of H, which is also a square root, which is also satisfied. That will, this is just the point is, it is not just in the C star algebra generated by that. Okay. So maybe remark. Okay, there is a definition I want to make. So you have positivity, so then we can compare self-adjoint elements. This is not a total order, but This is a partial order. The S and T are two elements in the B of H. They are self-adjoint. Okay. Then we say S is greater than or equal to T if S minus T is greater than or equal to 0 as operators. S minus T is a positive operator. That is S xi xi is greater than or equal to T xi xi for all z. That's what it means. That's what it means. This is the definition of, this is a partial order on self-adjoint elements. Maybe two things may not be comparable. Okay. It's not a total order. Okay. So now we will see this mark. So if you have a homomorphism between two systems, okay, in C-star algebra, you can define positivity. Maybe I should have defined the positivity as to be this. Okay, it's equivalent, but to make it define it for C-star algebra, T is a C-star algebra. Okay, just the same thing. A is a C-star algebra, and X in A is positive if there exists a Y in A such that X equal to Y star Y. Okay. If you want, you can write it like this. Okay. You can define positivity for a general C-star. Okay. Which is same, for B of H, it is for operators, it is this. Okay. So if we have a pi from A to B, is a homomorphism, star homomorphism. Okay. Star homomorphism. Then it preserves positivity. Okay. Then if X is positive, this implies then pi of X is positive. Okay. Of course, X equal to Y star Y. Then pi of X is equal to pi of Y, which is a star homomorphism, pi of Y. Okay. So it preserves positivity. So in particular, it preserves the partial order. If X is greater than or equal to Y, that means X minus Y is greater than or equal to 0. So pi of X minus, is a single homomorphism, then pi of X is greater than or equal to pi of Y. So if you have a homomorphism, it preserves the positivity. So we want to use this for the functional calculus, which is a homomorphism, of course. And we want to prove the following. So before that, I want to make a notation. This is just a sum of the positive elements is positive. We haven't proved. Huh? No, we haven't proved. Yeah.
Because in that too, like makes a valid part. That's what
Hmm?
you need to prove that for this is a partial because
Yeah, but for this, do we need it?
But we are partial in the first place.
Yeah, that's right. I'm just wondering. That's true, but we need to go through the proof. I'm just want to use this property. That's all. This, I'm just saying that if X looks like Y star Y, then this looks like this. Then if X is greater than, if X is greater than Y, what is the problem in that? X is greater than Y, then pi of X is greater than pi of Y. That's what I want. So we'll prove that later. We'll come to that again. But I just want to use this property. Yeah. I want to use this property. That's all. Yeah. We have to prove that if X, Y is positive, X plus Y is positive. We'll come to that later. For a general case algebra. Okay, so this is what I want to use. Okay. I want to use with that property. With this property. Okay. That's all. So this is a notation. We may not need it, but each time we don't want to write a range. So if we have a T in B of H, which is self-adjoint, okay, then we call this is MT of E. This something, the notation is flipped here, range of 1 ET. Okay. This is a subspace contained in subspace, closed subspace. So I'm just taking the range of 180 to be this. Okay. Okay. Then we have the following proposition. So for any set E, we can define this 180 and we can define this. For we want to consider, so these are what are called spectral projections. These are called spectral projections corresponding to the set E. Okay. So this is one proposition. One is, if you have a T, of course, T is self-adjoint always, self-adjoint. Then one, you take an interval which is maybe closed interval, a T. I think I don't know exactly. So for all xi in H, A times norm xi square, for all not in here, for all xi in this M T closed interval. Okay. Which is just the range of 1 ABT, norm xi square is less than or equal to E xi is less than or equal to B times norm xi square. Okay. This is one. Maybe you will prove one by one, and so that this will be used in the next one. So proof. So the function at function level, it satisfies the following. I mean, for all T naught, it satisfies T times 1 AB as functions. Okay. Maybe T is less than or equal to B, less than or equal to A, of course, as functions. So this implies A times identity. I mean, 1 is the identity operator. Okay. Identity is H. Okay. If you take the functional calculus, constant is constant. Okay. Identity is identity times T times, this is that 1 AB of T. This is a projection. Okay. 1 AB of T is less than or equal to B times 1 of H. Okay. Since the partial order is preserved under homomorphism, this is true. When functional calculus is homomorphism, and we get this. Now you take xi. I mean, now you take inner product with xi. Each one, I mean, that's what it means, no? S is greater than T if S xi is greater than T xi. So if we take the inner product, taking inner product with xi, we get that if no, now if xi is in range of that, which is that M of T of AB, then this acting on xi is xi, of course. So you take, so this implies T xi is greater than or equal to A of norm xi square is less than or equal to B of norm. Yes. That's all. So 2, this is just what we have done. That is, internet. Okay, this is clear. I will just write it. T of 1, 0, infinity, t. As an operator, this is greater than 0. Okay? This is since t of 1, 0, infinity, t. This function is greater than or equal to 0, right? This function, t times 1, 0, infinity, t. 1, 0, infinity is the indicator function of 0. This function is 0 when t is less than 0. This is greater than, I mean, this is equal to t if t is greater than 0. So this is, because of that, this is true. Okay. Then the third one is if xi is in M of P of this open interval, not open interval, open interval removed from this T0 minus epsilon, T0 plus epsilon. To take this open interval, T0 plus minus epsilon, T0 plus epsilon, remove it from R. So this is just all T greater than T plus epsilon, less than T minus epsilon, T0 minus epsilon. Okay. So when xi is here, okay, then so yeah, then T of T0 xi, and xi is here, is greater than or equal to epsilon times norm. That's all. Okay. Proof. Notice, I mean, from the assignment, because which is just an observation, one of this R minus T0 minus epsilon, T0 plus epsilon, this thing of any T is equal to T minus T0 square. Okay. One of this with epsilon square in the open interval, epsilon square infinity. Right? I mean, we just notice this, no? F of t of any f of t is equal to 1 of t f inverse e. Okay? So if you use that, t minus t square epsilon. So t minus t is between, I mean, t minus, that is between minus epsilon to epsilon. So this is greater than epsilon square infinity. Okay? This is by assignment. Okay. So now if xi is here, I mean, now xi is in m whatever, the t of r minus t naught minus epsilon, t naught plus epsilon. Okay. Then of course, then it follows that t minus t naught t minus t naught square xi is greater than or equal to that epsilon square xi square. And this is self-adjoint. So this is equal to norm of t minus t naught xi square is greater than or equal to epsilon. So this is true. Okay. And this is what we want. T minus T0 xi is greater than epsilon. This is what we want. Okay. So fourth one. So T naught is in sigma of T is equivalent to saying this M T of this open it. I think it is just T naught minus T naught. T naught plus T naught is not equal to. I mean, spaces cannot be, and this is non-trivial. Okay. So proof. So let f naught be the function, f naught t equal to t. This is the function on sigma of t. Okay. So T naught is in sigma of t is equivalent to saying f naught minus T naught is not invertible. Okay. This is not invertible. You can say, I mean, this is equal to saying T minus T naught is not invertible. This is equal to saying f naught minus T naught is not invertible. But f naught minus T naught, this is a function, this is scalar. This is not, of course, if it is not invertible in C of sigma of t, it just means that T naught is in the range of f naught t. But this is not invertible in L infinity. It's the same as that, right? So here the meaning is different. So by assignment, this is equivalent to saying mu of for all epsilon greater than 0, mu of what is that? F naught minus T naught less than epsilon is greater than 0, no? Less than epsilon is greater than 0, right? Right? This is the, given assignment, no, this is the meaning, right? Less than or equal to maybe, doesn't matter. So this says that this set one of t, where, the set where f naught minus T naught less than epsilon, this is not equal to 0 as a function. Mu of that is greater than or equal to 0 in L infinity means that this is not a 0 function. This is not the equivalence class of 0. That's what it means. So which is equivalent to saying that, so range of, you take the functional calculus, range of that is not trivial again. Okay? The functional calculus is isometric. It's isometric. So if this indicator function, this function is not equal to 0 means the projection is not equal to 0. So this means MT of this this function. For f naught t, if you just take just t minus, what do we want? We want to say that t minus t naught. We want to say that that is not equal to that, right? MT of this t naught epsilon naught, sorry, epsilon. Yeah, this is what t naught minus epsilon. This is precisely that, no? T naught plus epsilon. This is not the same. Yeah, this same mean, right? The range of that is this, okay, by definition. This is not equal to 0. So we have proved this. So here we are invoking the invertibility in L infinity and that we are using the functional calculus for L infinity. 5. Last one. One is kernel of t minus t naught is equal to take the singleton set. Okay. Kernel of t minus t naught equal to singleton, MT of the singleton set. This is a set. You have the, I mean, this is it. I mean, hope it's not confusing there. This is just the one T naught of T. Okay. This set corresponds to of those the measure need not be absolutely continuous with respect to Lebesgue measure, of course. I mean, even you can have eigenvalues, isolated eigenvalues, and measure can be concentrated somewhere. There's a proof of 5. One way. So we will first prove that MT of that singleton T naught is contained in kernel of T minus T naught. First we will prove this. So this is first to prove this. So we take a xi here. We take a xi here. This T naught is nothing but the interval, I mean, just a closed interval T naught, right? So because of that, we have the first equation, inequality, no? This is greater than a psi square, b psi square, a equal to b. So this has to be equal to that, right? When t psi is greater than this, t psi is less than this. Okay, when xi is in the interval a b, in the interval is same a. So this just implies that t psi equal to t naught times xi norm psi square. Okay, by 1. So this implies t minus t naught xi equals 0. So what do we want to prove? Yeah, equals 0. This is 0 for all xi in that whatever m. Okay. Now I want to prove that so xi is in the kernel of this. Okay. Remember that all our spectral projection, all our measurable, I mean, operators given by the measurable functional calculus, they commute with t. Okay, they commute with this also. T, they will commute with t and t0 also. I mean, we have a theorem, no? If something s xi equals 0 for all xi, then s is 0. We have a theorem. But here we have only for those kind of things. So in particular, we can have this says that t minus t naught into 1 of the singleton 0 t. I mean, you can bring it here also if you want. This is, I mean, square of this is same as that. So you can bring one of them here. This is just the operator restricted to that subspace. Okay. Equal to 0. This is for all xi. Is this okay? If you take any xi in H, then one t is xi is in that whatever that empty t naught. Okay. So for that we have proved this. So this is true. So this in particular implies that t minus t naught times 1 t naught t equals 0 as operators. Okay. I mean, if you have two operators, st equals 0 means the range of one of them, I mean, range of this is right, no, right hand side operator should be contained in the kernel of that. So this is range of this should be contained in the kernel of this. So this implies m t, this is the range of that. Okay, it's contained in kernel of t minus t naught. Okay. Okay. So we have proved one inclusion. Okay. Shall I repeat? Is it okay? I want to prove this is included in this. I take an element xi here. I mean, here I have changed xi for all xi. Okay, that I'll come to that because I'm using for yeah, you can take a 1-0 take here and bring it here. That's what I said. This is a projection and it commutes with this. Okay. So you can take it one of them here and bring it here. Okay. So that's all. Because it commutes and it's a projection. Okay. I mean, what I want to say is T minus T naught restricted to this subspace, and then Xi can be anything. And outside that subspace, it is zero anyway, operator. Okay. Yeah, good point. Okay. Yeah, but I said it orally, I didn't write it. So you can take it here and bring it here. So this is true. The statement is true. Yeah. So now we want to prove the other way. So to prove kernel of T minus T naught is contained in that M T naught. To prove this, so let us take a Xi here, and we want to prove that Xi is there. So this just means T minus T naught Xi equals 0. Okay. In particular, you can attach this one of we take a Xi here. Okay. Then this just says that T minus T naught Xi. This is the kernel means this is equal to 0. So you can act one of R minus this R minus T naught minus epsilon, T naught plus epsilon. Okay. I mean, anything you can act on this T equals 0. Okay. But then this commutes with that. Okay. So I can bring it here. I mean, I have swollen the T minus epsilon. There is a step. This is equal to 0 because you can take it there and because you can bring it here. Okay. This is equal to this. Okay. But then we have, did I erase this? Yeah, second, this thing. So T minus T naught Xi is greater than epsilon times Xi for all Xi in this here. Okay. So because of this, so this is an element. This is an element in there. Okay. So this implies one, this, I mean, norm of this. This is, I mean, this says that T minus T naught Xi is greater than or equal to epsilon times Xi for all epsilon. Okay. This is true for all epsilon. Okay. So there it says that T minus T naught of instead of Xi, you use this. Use this. Okay. This is equal to 0, it says. So, but then unless that is equal to 0, this cannot happen, right? Because this is true for all epsilon. So this implies that this is 0. 1 of R minus that T naught minus epsilon, T naught plus epsilon of T acting on this Xi equals 0. So this implies this belongs to the orthogonal complement of this. So orthogonal complement is the set complement. Okay, so this implies this is in T naught minus epsilon, the closed interval. T naught plus epsilon. Yeah. Closed interval is okay. Yeah. Sorry, the range of this. Okay. You will write it M. M of T of T naught minus epsilon. Okay. Xi is here. Now, this is for all epsilon. So this implies Xi is in M of T of this. Which is just this. So we have proved 5. I think that's all. I mean, this is like a lemma, but we have said it is a proposition. Okay. How tired you are? Shall I go through another proposition because you missed a class? You have a class, okay. So you need energy. Okay, I'll stop here. Okay, I want to use something called Halmos. This is the idea is Halmos. Next is whatever the proposition I'm going to prove is the idea of Halmos. So I will prove that, and using that we will prove the spectral functional calculus for commuting n tuple of operators, and any normal operator is two commuting two self-adjoint operators. So using that, you will prove spectral theorem for self-adjoint operators. That's all. Yeah, 6:30 is okay.